First off, we're going to talk about holes and all the things you can put in them. And don't worry, this is a family-friendly channel. We're talking about machinist fits. Okay. Now, you probably don't think about this, but there are different kinds of fits that are required depending on what you're trying to accomplish. And in the world of engineering, there is a whole host of properties that you can get through simple changes to the fit tolerance of a hole. For instance, let me put on my artist glove and we'll draw a picture here. What color should we use today? It looks like it's set to yellow, so I think I'll just stick with yellow. All right, so here we have a pin and the hole. And you can tell by the way that I've drawn these that obviously this pin is not going to fit inside this hole. And this is one of the most difficult fits to get. This is called an interference fit. And this is what you would use when you never want the pin and the hole to be separated again. There's a lot of good examples out there, but one that comes to mind is what you might find on a planetary gearbox for the axles inside of a drill. So depending on the make and model, a lot of times, in this case, you can see that these are clearly different metals for the axle and this carrier here. So this is probably a press interference fit. And so that's a case where they've undersized the hole so that the pin will never be able to escape. And there's a couple ways to actually get the pin into the hole. One thing you can do is you can chamfer the edges like so. And now this diameter is less than the overall diameter of the hole. And if you have this kind of allowance built in, if you have a strong enough press, you can just shove these together and you're going to get an averaging where the hole will have to stretch out a little bit and the pin will have to shrink some. Okay, that's one method, and that's used where the interference fit is relatively small compared to some of the interference fits that are possible. The next step up is you can actually heat the hole or cool down the pin. Mark Rober actually did a really good example of this with his ice cream container. And basically what you do here is when you have a metallic object, you can heat it up. So in this case, let's do the hole, right? And when you heat it up, it's going to expand. Well, if you can get that expansion to match the diameter of your pin, then it doesn't actually take that much force to get the pin into the hole. But what's going to happen when it cools? Well, it's going to want to go back to its original size. So the hole is going to shrink down around the pin, creating that interference fit. And I've got pulled up here the Class 5 Locational Interference Tolerance Chart for holes and bolts from Engineer's Edge. And this gives us an idea as to what kinds of interference fits are possible. Okay, so for a 1/8 hole, that's what this 0.125 denotes. The hole diameter is going to be undersized, so 0.124 up to 0.1248. And the shaft diameter, or the pin, is going to be oversized, 0.1254 and 0.1250. And that gives us a range of a maximum and minimum interference fit between 0.0002, or let's see, that would be tens, hundreds, thousandths, 2/10. I believe that's how you'd say it. I don't know. I'm not actually a machinist, so I'm still trying to figure out how they speak. And 14 thousandths, I think, is what that would be. But in any case, this gives you a range of what interference fits are possible. So like I was saying before with the simple press example, if all you're going to do is give the pin a little bit of a chamfer and try to ram it in with an arbor press, that's going to be on the lower end of the range of fits. So that might be your 0.0002. Whereas if you heat up the hole or freeze the pin, you can get a much tighter fit and use that higher end of the range with the 0.0014. But this isn't the only kind of fit that's out there. This is just when you don't want things to move at all. If we step down to class 4, medium running fit tolerances are intended for higher running speeds or heavy journal pressures or both. So these are parts that are allowed to move, and you want to constrain their movement. One thing that you'll see on a lot of different mechanical fixtures is a term called preload. You see this especially with bearings. And the idea of preload is that, let's say you have your bearing sleeve, and you have the inner sleeve, and then you have the balls that run in the middle. And do I happen to have a bearing near me? Doesn't look like I do. Dang it. If you're handling a bearing, you're going to notice that it doesn't perfectly constrain the movement the way that you might think it does. This is a pretty standard roller bearing, and it's going to have movement where the inner ring will be able to move relative to the outer ring. But then if we view this from the side, do like a cutaway here. Look how fast I am. If we look at it from the side, you might also get a case where it can move at an angle from the center line, right? So this is our line that goes through the axle. That's the line, that's the axis that we want to rotate around, but you might get an angle created by the movement between these various parts. Okay, so that's an example for a bearing, and the way that you fix this is you add compressive forces around the outside of the bearing and the inside of the inner bearing. And what that's going to do is that's going to take up any of the slop that the bearing has and force it to run in the way that it was intended to. And this is often a requirement for higher industrial grade purposes. Like if you're just designing a fidget toy, probably not that important, right? But if you need this bearing to last a really long time and do the absolute best it can in a very harsh environment, preload is absolutely going to be one of the characteristics you're going to look at. And we're looking at a very similar concept here with these class 4 holes. They are intended for higher running speeds or heavy journal pressures or both. So this is going to be a heavy duty spinning object that needs to be able to perform at a high level, and it needs to be constrained. The bad part about having this kind of excess movement, as we show in this diagram, is even if it's just a small angle, you could be creating a situation where you're generating a torque that adversely affects the system's performance. For example, let's consider a bike wheel. So again, this is a cutaway view going through the side. So you have your spokes, and they all connect to a central hub where they spin around the cassette bearing. Okay? If your bike wheel somehow bends such that it's now positioned like this relative to its cassette, that creates a torque through the middle of your cassette. And that could cause these spokes on the outside to stretch and tear. It could cause these ones on the inside to bend and kink, which also isn't going to be good. It could also be causing the, let's see, need to add another line to kind of imply it here, the rim of your tire to bend. And all of this is going to be really bad for your bike if it gets too extreme. That's going to mean that you need to get a new wheel. Not a good day. So if you constrain the movement so that that's not allowed, your bike is going to perform a lot better and it's going to last a lot longer. And one of the ways that we do that is you constrain the movement so that those kinds of problems don't arise in the first place. So having a tight-fitting bearing is one way to accomplish that. That's going to make it so that this case never happens. Now, if you've ever built something yourself, you're probably more familiar with the class 2 or 1 through 3 fits. And these are generally what people are going to be capable of creating with a simple drill. And you can see here, if we look at the clearance, now, see, this is the difference, right? When we looked at class 5, you were talking about interference. step down to class 4, now we're talking about clearance, okay? So now we are talking about a case where the pin is actually smaller than the hole it goes into, right? And we call the total distance that we've afforded ourselves, this is our clearance, okay? So that's what we're talking about when we look at this diagram. So clearance maximum and minimum, we go from 0.001 to 0.013 in the case of a class 4, but with a class 3, we can see that it gets significantly larger, right? And that's with the 1/8 hole. If we step all the way down to a class 1, now we've got a clearance of 0.0004 up to 0.0022. So again, this distance that I have highlighted here in yellow, you take this plus this, and that can be between 0.0004 to 0.0022. And these are in inches, by the way. And one question that arises from this is, well, why do we have a range like that? Why isn't it always just a set value? Why do you need to specify that it could be as low as this and as high as this? And if we were to zoom in on the surface of our metal, in fact, let's do that. Let's look up a picture of steel under electron microscope. You might think that metal is smooth, but it's actually not. It can be very rough indeed. That's not quite what I'm looking at. Oh, these are always cool. This is what it looks like when you're shaving off steel with a cutting bit, by the way. Everything is a goo. Everything in life is a goo. It just depends on how much force is applied. That looks like brushed steel. That doesn't look like milled steel. Here we go. This is what I wanted. Okay, so these circular or radial lines, this is from a fly cutter. And let's show what a fly cutter looks like. You basically have a large spinning disc, and you put a cutter at the end of the disc, okay? And then this is your spindle that goes up into the machine. We'll talk about why these are slanted in a minute. That's a very important feature on a cutter called a taper. But as this gets spinning around, so it's spinning, this cutter is going to leave those kinds of patterns on the steel. And if the cutter was moving across the steel from right to left, so it's been moving this way, that means that there's sections of steel over here that have already been hit once with the cutter when it was over here. And then on the trailing edge, you'll have these forward lines overlapping the rear lines. Okay, so if we look at that picture again, we see that that's exactly what's happening. You have crisscrossing circular lines. Okay, if you touch this, it's going to feel very flat. You're not going to be able to pick at these with your fingernail. It's going to feel smooth to the touch. But what's going on at a microscopic level is it's entirely impossible to get a perfectly flat surface. So this line represents the ideal. And what we actually get is something more like this. So the average, it might be the ideal that we're looking for, but the reality is we're still looking at several peaks and valleys. Okay? Now let's look at a drill bit and see how that might affect this. So there's a good picture. You can see that you don't have a, like if we were to take our hole, and this is our top view, right? And we want to say this part of the hole right here. And we're looking at a line going down this hole. So from a different view, that would look like this. And we want to look at a line right here. Okay, if we look at our drill bit, we see that it does not make constant contact, right? It's going to make draw a really big drill bit here. It's going to have a gap here, and then it's going to have another one further up. And so it's not going to be making perfect contact. that alone adds some variance to how the cut is being made. And the other aspect is the drill bit itself is not going to be perfectly straight, nor is it going to be perfectly rigid. So this becomes a problem when you talk about really deep holes. You can actually get the drill bit to wander a bit. And then if your intended hole was supposed to be straight down like this, pretty soon you're in a world of trouble. If you need a better surface quality on your drill or on your hole, then you use what's called a reamer. And these are going to be one of the more common types that are out there with straight flutes. There we go. There's a better picture. So it's a big, long, straight flute, and you actually use this to finish a drilled hole. So you start with a hole that's slightly undersized from what you want, and then you have your true hole size that corresponds to the diameter listed by your reamer. So you drill the hole first, then you come in with the reamer, and that's going to give you better surface quality and a more accurate fit for the hole. And when you're talking about doing press fits and those class 5 and 4, you're typically going to be doing those with a reamer because you need to know that the diameter is exactly what you specified it to, else you're not going to get the level of retention that you need for that hole. But again, if we zoom in on the side of our hole here, we're going to see that that surface is not entirely smooth. It's still going to be rough. And so one thing that these different fit tolerances allow us to do is we can take the average line of two pieces of metal and push them together by a specified amount. And that's kind of what we're trying to do with these different fit tolerances. So if I have, that's my hole surface, and then I have my pin surface, and it's something like that, just maybe when I press them together, I get the best of both worlds and I get a good fit, a straight-ish line. That's part of the idea with an interference fit. And then when you're talking about rolling resistance, you're just trying to get them close enough that they are able to make enough contact to keep each other constrained. So why am I thinking about holes so much? Well, one, I'm a man, and I guess that's what we tend to do. But the other part is I've been working on what's called a tool changer for a 3D printer. What you see here is not my design. This is a really cool design made by not that bank of tabs. This bank of tabs, Draft Shift. I think that's the name of the guy. And I just realized I'm not actually listening to anything in those, so I don't need to have those on. This is his stealth changer, and I should probably make the camera bigger. Let's see. Drill bit suffered more from wobble, which causes runout or circularity issues. Absolutely true. Yes. Surface finishes improved with reaming and boring. Yes, those are both very good points. So what Mr. Arrowhead is pointing out, and I closed them, but the reamer is going to be much more rigid, so it's going to stay straighter in the hole. It's also removing significantly less material, so there's less stress on the reamer compared to a drill bit. Drill bits are really good for removing lots of material rather quickly, but they're going to be more flexible, which is going to cause deflection. They're going to wobble, and they're going to have runout. Runout is the side-to-side movement of a tool, and all of that contributes to the hole not being quite the way you want. Here's actually an article that I had pulled up in preparation for that, kind of showing the types of errors you can get. So with this first image, we're looking at something that has very poor circularity, right? This is a potato. You would not even call this a hole, right? But keep in mind that this is dramatized for effect. Each of these grid squares is 100 microns. Yes, I think that's right. Symbology. So these are teeny tiny differences. Right? Another issue that you might have is it might not be in the exact center of where you need the hole. This is like what we've talked about in other videos where you have accuracy versus precision. If you're extremely accurate, your average hits will be centered on your target, right? But if you're not precise, then you could be all over the place. But as long as the average is over the bullseye, that's accurate. Or you could be precise, where all of your hits are very close together, but if you lack accuracy, you could be off in the far corner of your target, right? Same thing applies here with the drill. If you are off from where you are intending to drill the hole, you are not accurate. But if you have really good circularity, you might say that you're very precise. But you want to have a combination of the two in order to get the properties that you want for the project you're working on. And then when you come back in with a reamer or boring bar, which is what this is. So basically you'll have either, depending on the machine you're using, right? Because a mill spins the tool and a lathe spins the workpiece. So if this were in a lathe, this would be stationary, and you'd have your hole spinning rapidly around the boring bit, and then this tiny cutter head is creeping up to the right dimension that you're looking for. I took a CAD CAM class, and so I know the very basics, but everything else comes from watching other people on YouTube. But you will get quite a bit better surface quality using either a reamer or a boring bit. Because the boring bit is still a small section is being removed in a line, and if you're going too quickly, you can still get the same kinds of errors that you see with the fly cutter example, where you might be causing pits and valleys, hills and valleys, based off of where the cutter head happened to be at the time. So boring operations, you're going to tend to be moving very slowly in and out of the hole, while the workpiece is just going to be like ripping around, or vice versa. Basically, the depth inside the hole is not going to be changing very quickly when you're doing a boring operation, because you want to minimize that kind of error as much as possible. But back to this thing, and I forgot the reason why I had pulled OBS up was so that I could change the dimensions of the camera a little bit. There we go. So this is the Stealth Changer by Draft Shift. And the purpose of this is you would mount all the needed parts for a 3D printer tool head onto this gray carriage here. This is printed out of PETG, or carbon fiber PETG, and it's removable from this aluminum fixture plate. I got this off of Fabrico. They are a online 3D printer part retailer. And now that I have this off, I'm realizing that I don't have anything constraining it to the linear rail. So if I flick this off too far, I could actually cause myself a world of pain where all the ball bearings fall out. So let's hope I'm careful about that. But let's take a look at how Draft Shift has designed the fitment of his carriage. You can see he's using 3 locating pins, and these have a rounded head. And then he's further enhancing the fit with 3 magnets. There's 2 screw heads towards the bottom, and then there's a magnet here in the middle. If I show you the fixture plate, we see the inverse. You have 2 magnets on the bottom and a screw on the top. And those are working together to create what I think is a pretty good fit. So you get them lined up, and then the magnets kind of take over for you, and they get this thing planted fairly well. The problem is, there is still some wobble in a design like this. And the way that Draft Shift is mitigating that to a degree is through the use of the screws. So you're actually instructed to back these out or tighten them up and in order to get the best fit. So that's one way to adjust it. You can also tweak the position of the pins, but you don't have a lot of adjustability built into those pins. The primary adjustment mechanism is through those screws. Okay, now I want to be really clear. This is an awesome project, and I don't in any way mean to bag on Draft Shift. I think that this is a fantastic basis. I just think that it could be a little better with the locating features, and that's where tapers come in. So tapers are magic. let's go back to our drawing and think about all the kinds of errors that we can have with holes. Okay, so there's our hole. Okay, so in theory, we could get a pin that exactly matches the diameter. And suppose we use very high lubricity materials and we get it such that the surface quality is immaculate, right? We could have a situation where that pin would perfectly fill that hole. But we already know that that's probably not the case, right? So there's going to be side-to-side wobble where, let's say that the pin is perfectly parallel to the hole, but because its diameter is off, there is some amount of movement that it can make side to side, right? And I'm trying to think of a way to show this without it looking crude, but I don't think that there really is another option. Hole, pin, wobble, right? Not good in the case of a locating feature. We want that to be reduced. So you want to use a pin that is as close to the diameter of the hole as possible. Another kind of error is you can have it be tilted. And as gamers, we should all know about being tilted, right? We're tilted most of the time. And that's where the axis of the pin is not parallel to the hole. And this can especially cause binding, right? Imagine the corner of your pin hitting up against the side of your hole here. If you're trying to push that pin in, you're going to be scraping those materials against each other, and you're going to have a pressure concentration at that corner, and that's going to cause some significant binding. If you imagine also rotating this pin, you have another contact point over here where it's just going to be rubbing in a really bad way. This is not the good kind of rubbing. So that's another kind of error we can have. You can also have issues where depth is a concern. These aren't as critical for the most part, but let's say your pin is not as long as it needs to be, and so there's some distance where you're bottoming out before you get to the bottom, or you could have the inverse. The pin could be too long, and so you bottom out before you get to the top of the pin, right? Both of these are potential problems. But what if I told you that there was a way to fix this most of the time? That is where you have something like tapers come in. And before we show the magic of that, there's one more thing I need to show you, and that is how you can have a situation where you actually get very minimal contact between straight-walled holes and pins, right? We've already talked about our microscopic surfaces and how if you zoom in, you're gonna see hills and valleys, right? Well, you could have a perfect storm where only the hills are touching, and that results in very minimal contact between both the pin and the hole. And if we're talking about locating something, we want to maximize that contact because that contact is what's going to keep things from moving around. So what happens if we take those same imperfect surfaces and we put them at an angle? What do you think is going to happen? Well, if we are concerned about contact, we can always just push the taper harder and we can increase the contact by brute forcing it. That's one thing that we can accomplish. And the greater the surface contact between the taper and its hole, the more grip that the hole and taper are going to have on each other. And a perfect example of this is CNC tool heads, or I should say holders, right? I should have stayed back here. Let's do the image search. So if you've only ever used like a drill bit, this actually seems kind of counterintuitive, right? Because you look at your drill bit and you have that hex-shaped pattern, and it makes sense why the drill bit is able to be driven, right? The drill is simply grabbing onto it, usually with 3 lobes, right, in most drill trucks, and it's twisting the drill bit by grabbing the flats, right? But then you look at a CNC tool holder, and it's like, where's the flats? There is none. And what's actually going on is these are so precisely machined that if you hold the holder, which is this part, in its spindle, which is going to be the large motorized piece of equipment that holds all of this, They are so well machined that they make the maximum amount of surface contact that we have been able to achieve as humankind. You can take a Sharpie and scribble all over the sides of your holder, and if you spin it around inside the spindle, the Sharpie's going to get rubbed off, right? We're talking like that level of precision. It's really something beautiful. And that insane amount of surface contact allows these cutters to be driven at really high torques and speeds without slipping. There's another important detail about this, though. If I have, because that's how we get precision with like a CNC machine, right? But what if I have only the ability to make a reasonably good straight walled hole, right? Something like this. We know that if we have a straight pin, we can have all those errors we mentioned before, where the pin might not be parallel to the hole, or it might have side-to-side wobble. But if we talk about a tapered pin, when we're talking about the side-to-side wobble, well, it will simply sink into the hole to the point where the side-to-side wobble is eliminated. And as long as we have reasonably well machined carriages for the taper, we can do a pretty good job of ensuring that the axis of the taper pin is also going to be parallel to the hole. And so what you get with a tapered pin and a straight walled hole is you get a self-centering mechanism. And so these are something that you can buy on McMaster-Carr. I don't need that one anymore, or that one. We need to keep that closed. These are something that you can get in McMaster-Carr, and these are commonly used for aligning all kinds of things, especially in the industrial world, like tool dies, stamping dies, things like that. Anything that is going to be repeatedly put together and then taken apart, you're pretty much going to see a tapered pin on all of those, because a straight pin is just too much of a headache most of the time, and it doesn't guarantee the fitment that you're looking for, but you can almost guarantee it all the time with a tapered pin. So let's see. Locating pins are a good example. These ones are ones that come with a shoulder, right? So you have a shoulder, and then you have a little tapered section there, or probably not on those actually. Those are probably more geometrically based. You can also get these threaded taper pins, right? And so you could screw these directly into whatever you're trying to align with something else. That's funny. I don't think I've noticed these on McMaster-Carr before, but that's a little scale image, I guess, for you. So if you hold your hand like this, then you could get a good scale reference. I guess you could look at your friend's hand, or you could probably just make an assumption based on your other hand. But you can also get tapered pins from Misumi. I found this somewhat recently. I don't want to log in though. I just want to go to the website. There we go. And what I like about Misumi is, at least in the realm of tapered pins, I found that they actually have a wider selection compared to McMaster-Carr, and they tend to be a bit cheaper too. So you buy them based off of what features you're looking for, and then you narrow it down based on size. So let's look for something that looks like what I had in mind, which I think is going to be these, right? Then you go through their configurator, and this is actually a really nice configurator too. I'm not sponsored by Misumi. I highly doubt they sponsored that many people, but I've been able to find the parts that I've been looking and designing for very easily using this configurator. So these are something that you can get your hands on, right? It's not egregious, and if you go through Misumi, it seems to actually be fairly cheap too. But if we simply replaced those 3 pins with tapered pins, you would get all the benefits of tapers that I've already mentioned here, and it would basically eliminate any need to adjust this ever. And so when you're talking about a tool changer, well, you have multiple tools, right? And so not having to adjust any of your tools, that's a huge benefit. It gives you the ability to just say, yeah, it's going to work every time, and you don't have to worry about it. So tapered locating pins, draft shift, if you happen to be watching, might be something you want to implement. But If not, someone I know is also working on something that aims to do just that. So I want to show you what I've been working on for my SB08. I've been playing around with different designs for a tool changer myself. And the difference between what I'm doing and what other tool changer designs have done thus far is I don't want to make the whole tool head be what changes. I just want to focus on changing the hot end and the filament path only, right? So let me show you two very important pieces that I have here. These are the filament guide nuts for a Orbiter V2 extruder that were very kindly sent to me by Bondtech for the purpose of developing my tool changer. And if I show you really close so that you can get an idea of what I'm holding, got a little small taper. That's to get it in between the gears as close as possible. And then it's got a very precise hole for the filament, a threaded body section, and a slot for screwing it into whatever you're trying to mount it in onto. Okay, and if you have two of them stacked vertically with just a small gap for the filament to go between them, what you essentially have made is a flosser. And if you push that into an extruder, you can force the extruder to take on a new filament, assuming that, you took out the old flosser, right? So essentially what I'm trying to do is make a mounting system for just the hot end with the filament coming out of it. And then I'm going to redesign the orbiter to be able to be forced open and accept new filament paths. The benefit of a design like this is it's going to make it so that instead of changing the entire tool head, you'll just be changing the hot end and the filament, which means that you save a lot of money when adding more tool heads. Currently, you're looking at anywhere from $150 up to $300 in some extreme cases to add another tool to a tool changing setup. That's a big part of why a lot of people don't want to go the tool changer route, is because of that huge cost. It's something that keeps the Prusa XL from taking off and being more mainstream, because every time you want to add another head to your XL, it's going to cost you a pretty penny. But if you can make it so that you're just changing out the hot end, then you can save a lot of the initial cost of that setup. So that is ultimately why I've been learning about pins and tapers. And this is very similar to how the Bondtech index will work, as Mr. Aero Capital Fellow points out. But the Bondtech index uses a proprietary hot end and an induction heater, hence index. That's where they get the name, is the induction heater part. But that locks you into using only Bondtech parts, and you have a case where, at least in the 3D printing hobby space, you have people who have a lot of hot ends already. And so while I think that the Bondtech index has a lot going for it, and it definitely serves a purpose, it doesn't do much to recycle any of this older existing equipment. And if you've already bought into an ecosystem of nozzles and filaments and all this different stuff, you have this stuff lying around, you don't want to just toss it, right? You want to get use out of it. It also puts a restriction in that you're relying on Bondtech to come out with all the equipment that you may need quickly enough for you to be able to continue your workflow. So am I going to be able to outpace them? I don't know, probably not. This project has already taken me a lot longer than I thought it would. And you guys have seen how I am with all my other projects. On the personal side, I do struggle to finish. But this is something that I'm working towards. And if I can pull it off, it will allow you to use your existing hardware, as well as open up the possibility to use any other hardware that's out there, as long as it fits inside the tool changer carriage system, which should be pretty forgiving. But I think that covers the discussion for tapers and pins and holes. I think we've adequately covered holes and all the things you can put in them. So if you came in for just that on the stream, I hope you're well served.